Hey guys, in this video I wanted to work some practice problems related to the acylations of nucleophiles or nucleophilic acyl substitution. You'll hear me use both terms kind of interchangeably, and we'll talk about why these reactions are called this way in this video. And this is going to be related to LTQ 7.1 from the spring 2024 semester. So acylations of nucleophiles, in general, the idea is we're installing an acyl group at a nucleophilic atom. Nitrogen, oxygen, sulfur are probably the three most common. And we do this using an electrophilic carbonyl compound that's typically a carboxylic acid derivative, where the carbonyl group is connected to a leaving group, a group that's going to depart with a pair of electrons, typically form a relatively stable anion and that kind of thing. And we know in general that this mechanism goes via nucleophilic addition to the carbonyl group, followed by beta elimination. And sometimes this is mediated by acid catalysis. Sometimes this can just be done with a base around to remove a proton from the nucleophile if our carbonyl compound is very electrophilic. So in this first problem, we're going to predict the major neutral product of the reaction. And here, it's very important to keep the fundamentals in mind, apply your mechanistic reasoning, think carefully before you launch in and just kind of start drawing stuff. And right in this first example, we're immediately at a carbonyl compound that to the uninitiated looks very cryptic. This compound with two carbonyl groups and a central oxygen atom and two ethyl groups on either end. Now, this is known as an anhydride or an acid anhydride because if you consider the molecular formula of this relative to two carboxylic acid molecules, this is missing a molecule of water, and anhydrides can be made from carboxylic acids by dehydration, removing water. The anhydride gets confusing because there are two carbonyl groups in the structure, but the right way to think about this is as a carbonyl group connected to a carboxylate leaving group. So for example, we can think of the entire right half of this molecule as a carboxylate leaving group, and you can imagine if that entire fragment in orange leaves, we're going to end up with a carboxylate anion, relatively stable anion, resonance stabilized, all that good stuff. Carboxylic acids are pretty acidic. This all adds up to this portion of the molecule can act as a leaving group. This means that the other carbonyl carbon we can think of as an electrophile, and this entire molecule as an acylating agent, where what we're doing here is we're installing this acyl group on a nucleophile in the substrate. Now, of course, it's completely fine because this is a symmetric anhydride to think about the left half as the carboxylate and the right half as that electrophilic acyl group that we're installing. The two approaches are equivalent here. So we've identified the electrophile. It's this carbonyl carbon connected to a good leaving group in the carboxylate. Where's the nucleophile in our substrate? Well, pretty clearly, it's going to be the nitrogen, right? We've got a lone pair on that nitrogen that's we know is relatively Bronsted basic, also a good nucleophile. And the idea of nucleophilic acyl substitution is very similar to other nucleophilic substitutions you've seen, where the pattern is identify the nucleophile, identify the electrophile and the leaving group, and use the nucleophile to displace the leaving group. So keeping in mind here that the mechanism is addition-elimination. It's not SN2, SN1. That's why we use this SNAC label to basically stand for addition followed by elimination. We can kind of do the typical nucleophilic substitution dance where we lose a proton from the nucleophilic nitrogen, and that's going to leave us with one H remaining on that nitrogen, and we're going to add the electrophile there. Now, again, what is our electrophile? Well, the electrophilic atom is the carbonyl carbon, and the first step of this mechanism is something along the lines of this nitrogen adding in at that carbonyl carbon. And so the electrophile we're adding here is an acyl group. It's an acylation reaction. And notice we've made a bond between the nucleophilic nitrogen we identified previously and the electrophilic acyl carbon. Now the byproduct of this reaction, one thing we should notice is that, okay, a proton or hydrogen has disappeared from the nucleophilic nitrogen. Where did it go? Well, that's the purpose of the triethylamine. That will remove that proton and form HNET3+. Now that's a cation, and we need to balance that positive charge with negative charge somewhere, and given that we previously identified the carboxylate anion as a leaving group here, that's going to be our anion, right? That group will depart, taking a pair of electrons with it, and we'll end up with this carboxylate anion, and ultimately this sort of ammonium carboxylate salt that's going to be washed away in workup in the aqueous layer, and we're left with our amide in the organic layer as the neutral organic products. So these byproducts, not necessary to draw, but useful to keep in mind because they give us insight into how the mechanism proceeds, which helps us predict the product, right? All right, second case here, we've got an ester, and that ester is being treated with acidic water, essentially water as a solvent with some H2SO4 around. Now, water we know as a nucleophile, and the H2SO4 we know is something that can protonate things, and so I'm thinking about things like protonating the carbonyl oxygen because I have acid around. This creates an awesome electrophile at the carbonyl carbon. What nucleophile do I have around? Well, I have water. Let me do that water in purple. I've got solvent quantities of water around that can add to this now very electrophilic carbonyl carbon. And this kicks the mechanism off. This is going to create a new oxygen carbon bond. And ultimately what we're going to do here is lose methanol from the starting ester. The OMe group is going to be replaced with an OH group from water. So our product here is going to contain that cyclopentane ring, absolutely nothing different there. And after addition to the carbonyl carbon, followed by some proton transfers and elimination of methanol, we're going to end up with a carboxylic acid. And this is an example of a hydrolysis reaction. It is a nucleophilic acyl substitution. The mechanism is addition, elimination, both steps catalyzed by acid. And if you need to review this mechanism, I encourage you to pause and think this through. But the overall result is the substitution of water here for methanol. Essentially, methanol departs, water comes in. And so the byproduct here is MEOH, or methyl alcohol. In this third reaction, we have a cyclic ester, which is also known as a lactone, being treated with diisobutyl aluminum hydride, or DiBal-H, at negative 78 degrees Celsius, followed by our typical aqueous workup, which is typical for these reactions that involve reducing agents where we're going to generate an alkoxide. Now, we're familiar with DiBal at negative 78 as reducing esters to aldehydes. But in this particular case with a cyclic ester, it's very important to think this through mechanistically. One thing we should notice, for example, I'm going to move this last reaction down a little bit, is that after the initial addition of hydride here, we end up with an alkoxide anion that can kick off a leaving group that is still tethered to the aldehyde group that's going to form. So how did we get here? We got here by adding the hydride built into DiBal-H to the carbonyl carbon of the lactone here. That's an electrophile, and DiBal-H contains nucleophilic hydrogen, and so we add in there, get an alkoxide anion like so. But like we've seen with a number of different carboxylic acid derivatives at this point, this can kick off a leaving group. And when it does so here, this is going to produce an alcohol group or a hydroxyl group that is still in our molecule. So we still need to be thinking about what's going to happen at this point. So we've generated the aldehyde. That's our typical carbonyl reduction product of DiBal-H, but there's still an O- in the molecule. Let me redraw this a little bit so that I can make that H a little bit bigger. So we have this now, and then on aqueous workup, well, this is where we're going to protonate that O- to get the final product. So typical proton transfer to get the final product is going to give us a neutral product containing an aldehyde on one end and an alcohol on the other. And this is our final product here. Now, interestingly, one thing that I saw here that a number of people did, which is completely correct and may have been accidental, but still works, is to draw the hemiacetal formed when this hydroxyl group cyclizes onto the aldehyde. So the clever will notice that, hey, this can add to the aldehyde, and that makes a six-membered ring. And in fact, that hemiacetal formation may be highly favorable because we're making a six-membered ring, we're making a CO single bond, etc., right? And so a number of people drew this. Some people even added stereochemistry here because, hey, that is a stereocenter, and this is completely fine as well. In fact, this is likely to be the major form of this molecule in solution just because that cyclization forms a six-membered ring. So either the structure in purple or the structure in black are completely correct here, as far as I'm concerned. All right, last case, we've got a nucleophilic acyl substitution with a nucleophile that is a carboxylate. So we've got an O- there, although it is important to notice this is a resonance-stabilized anion. And we've got two potential electrophiles here, carboxylic acid right here, and an amide right there. One thing with nucleophilic substitution reactions in general, they will only work if our nucleophile is stronger than the nucleophilicity of the leaving group that departs. And so if we kick off a leaving group that's a stronger nucleophile than the reactant we're using or reagent we're using, that's not going to be a thermodynamically feasible process. Delta G will be greater than 0 and the reaction will be thermodynamically disfavored. That's what's going on here. If you think about the leaving groups that would be involved, if, for example, we attacked at the amide carbonyl carbon and then kicked off a leaving group, we'd be kicking off a nitrogen anion, and that's way less stable than this carboxylate nucleophile. So that's heavily disfavored. If we, on the other hand, thought about kicking off OH-, well, again here, that OH- is quite unstable relative to this resonance-stabilized carboxylate anion. So regardless of which carbonyl group we attack at here, or we add to do a substitution reaction, we're going to end up kicking off a leaving group that's less stable than the nucleophile we started with. This means that no reaction will occur in this case. In fact, the only thing that's going to occur is proton transfer between the carboxylic acid here in the substrate and this carboxylate anion. And this may or may not do anything, right? This looks like almost a 50-50 proton transfer with the carboxylic acid giving to a carboxylate. And so no meaningful reaction is going to occur under these conditions. This carboxylate nucleophile is too weak to displace either of the leaving groups that exist in this substrate. In this problem, we're looking for reagents that will accomplish each of these syntheses in high yield and, if necessary, high selectivity. In the first example, we've got a cyclic anhydride. Notice two carbonyl groups connected to a central oxygen. That is an anhydride. And this is opening, the ring is opening to form a diol. So the number of carbons is the same. We've got 1, 2, 3, 4 carbons here, 1, 2, 3, 4 carbons in the product. And one thing we should notice is that these carbons that were the carbonyl carbons in the reactant are adding H's and losing the carbonyl, the CO double bonds in this reaction. This corresponds to reduction, right? We're replacing the CO bonds in the reactant, specifically here and here, with CH bonds. This is a reduction process, and so we need a reducing agent to accomplish this. A number of people just used acid and water, reasoning that hydrolysis is going to open the ring, and that is true. Hydrolysis will open this ring. The issue with that is this does not do the required reduction, right? We would end up with two carboxylic acid groups in the product of, say, acidic. You wouldn't even need a catalyst here. Just treatment with water is going to produce this diacid, not the desired diol. If we want to get that diol, we've got to reduce either this or the starting anhydride using some kind of reducing agent here. And this is a case of go big or go home. You might as well use something like lithium aluminum hydride, LiAlH4, to completely reduce the anhydride, and then make sure to include aqueous workup to get those protons on the alkoxide anions to make the neutral diol product. So key here was to recognize that a reduction needs to occur, thinking about oxidation state logic, oxidation number, that kind of thing is going to be helpful for this. And then using a reducing agent that can actually accomplish this. Dibal at room temperature may be able to do it, but lithium aluminum hydride certainly is reactive enough to make this happen. And the initial hydrolysis is actually not even necessary. And so all we really need to do here is just use lithium aluminum hydride and water, starting with the anhydride starting material, and this gets the job done. All right, what's going on in the second case? Well, the change here is pretty straightforward. We're replacing an OH group with an NH2 group. A number of people just tried to use NH3 for this purpose, and I don't like this. Thermodynamically, it works in the sense that OH minus is more stable than NH2 minus, of course. But the problem is that this is going to do proton transfer, right? I've got an awesome base here, got a great acid here. We're going to transfer a proton from the carboxyl group to the NH3 and get an ammonium carboxylate. If you heat the crap out of that and wait long enough, it will eventually form the amide, but it's not ideal. There's a much more straightforward way to do this that works much better, and it involves converting the OH group in the starting carboxylic acid into a good leaving group. And the simplest one that we might think about, and one that is going to work every time, works like a charm, is chlorine. So we can think about making this turning this rather into an acyl chloride, and then just hitting that with NH3 using 2 equivalents of NH3, since one of those is going to sort of be used to mop up protons in the reaction mixture, and that would form this amide. Now, how do we make an acyl chloride from a carboxylic acid? For that, we use thionyl chloride, SOCl2, and this will replace the OH group of the carboxylic acid with a chlorine. Also works on alcohols, incidentally enough. So the idea here is, again, step 1, SOCl2, and then step 2, 2 equivalents of ammonia NH3. And of course, this will work with a primary amine or secondary amine as well. We don't have to just use NH3 if there are substituents on this nitrogen. All right, here. This third case is interesting. There are a couple of different ways to do this, and I'll tell you guys about the way I thought about doing it, although there is an alternative that I'll briefly mention at the end. So we're starting with iodobenzene. Intrinsically, iodobenzene is electrophilic at this carbon link to the iodine. Iodine is a good leaving group, right? Making that carbon a good electrophile. But it's not a great electrophile, right? Since this isn't a very electron-poor aromatic ring, we don't want to destroy aromaticity and all that good stuff. And so iodobenzene itself is not going to be super helpful for us, but we know we need to do something with that carbon bearing the iodine, right? Because there are 2 phenyl rings in the target that clearly have to come from this reactant. What we can think about doing with this then is turning it into a nucleophile at this carbon bearing the iodine, and we now know a way to do this using Grignard chemistry, right? So we could, for example, turn this into a Grignard reagent, and now we've got a good nucleophile. Now we've turned that carbon into a much more reactive carbon, right? And it's nucleophilic. This is going to inform what we do in the next step. But we now know we can use this for chemistry. And to do this transformation, all we need is magnesium metal. This would be done in diethyl ether solvent or tetrahydrofuran solvent, something like this, right? All right, what do we do with this, and how does this get us closer to the target? Well, we've got 2 phenyl groups connected to a central carbon in the target. And that central carbon we need to think of as electrophilic, right? Since the phenyl ring we've rendered nucleophilic, we want complementary reactivity in whatever reactant we use at this stage. And there were 2 approaches for this, and both of them work completely fine. One approach is to use a carboxylic acid derivative, such as an acyl chloride, anhydride, or ester, that does double addition of Grignard reagents, where one carbanion, if you like, adds in, and then we kick off the leaving group, and then a second adds in, and we get a tertiary alcohol. So my thought here was we could use something like ethyl acetate, or really any acetate ester. Since the OR group is going to get kicked off, it doesn't matter what ester we use here. And following that up with aqueous workup is going to take us directly to this tertiary alcohol product. This is the double addition of Grignard reagents to carboxylic acid derivatives that we've seen previously. Now, a number of people cleverly, and this is completely fine, incorporated the other phenyl ring into this electrophile and used acetophenone, phenyl methyl ketone, instead of an ester. That's completely fine as well. That's going to work great. There was no restriction on what you could use in this problem, and so that works completely fine as well. In this last problem, we're supposed to design a synthesis of ethyl acetate using acetic acid as the only source of carbon. Now, this latter bit is important. We need to use reactants containing carbons such that all those carbons came from acetic acid. Acetic acid contains 2 carbons, but ethyl acetate contains 4 carbons. And so we're going to need to first of all incorporate at least 2 molecules of acetic acid in the synthesis. I'm going to go ahead and copy this, since by this sort of carbon logic, we figured out we need to use at least 2 molecules of acetic acid in different ways, since carbons 3 and 4 are very different from carbons 1 and 2. So we're going to need to do some independent manipulations and then bring together the results of those manipulations to make ethyl acetate is the idea here. Now, carbons 1 and 2 look almost identical to the carbons in acetic acid. Carbon 2 is still a carbonyl carbon, carbon 1 is a methyl. Things look exactly the same. Carbons 3 and 4, though, look a little bit different, and in particular, carbon 3 actually looks like carbon 4 as I've numbered it. So let me redo the numbering here. It makes sense that this methyl group would be this methyl group in acetic acid. This gets turned around for reasons that we'll see in a second, but we should notice that what needs to happen, again, at carbon 4 is reduction needs to happen. And the reason this needs to happen is we're only able to use acetic acid, right? We are only able to use acetic acid as a source of carbon atoms. So we need to turn acetic acid into a reduced form with a CH2 where the carbonyl carbon is in the original molecule. And we can do this using lithium aluminum hydride. Actually is the best choice here. Why not go big or go home, right? We can use lithium aluminum hydride because we're not concerned with partial reduction. We want to push this thing all the way to the product alcohol, the primary alcohol with a CH2 group where the carbonyl group was. Go big or go home here is the name of the game with this reduction. One thing we can also note at this point is we can make this ester by combining the ethanol that we just made with acetic acid. And this is an example of a Fischer esterification process. We would combine these 2 reactants in the presence of an acid catalyst, H3O+, and this will give the ester product, particularly as we may take steps to remove water or use solvent quantities of the alcohol or both to drive this reaction to the ester product. But notice, this reaction is just a combination of acetic acid, which we're already able to use, with the ethanol that we made right here. And so another way we might write this, if we just kind of rearrange things a little bit, is we take this ethanol and we treat it with acetic acid and the acid catalyst. And at the same time, water is removed. So this is just a rearrangement of what we already noticed. And the idea here, again, the key idea to notice is that a reduction is necessary. And it's important to do that reduction before you do the acylation, essentially, of ethanol. We need to do the reduction first. A number of people made the anhydride first, so brought these together and made acetic anhydride, and then tried to selectively reduce one carbonyl group or the other, and that's just not going to be possible. Thinking about, as I called it, this kind of hyper-selective reduction, where we're asking nature to take something with two equivalent carbonyl groups and two highly reactive carbonyl groups and just turn one of those two into a CH2 is not going to be physically possible. This would react further, right, with essentially any reducing agent. This is, first of all, not going to give an ester. This will give an aldehyde before it gives an ester, and all that good stuff. Probably go all the way to the primary alcohol. And even if you could make this, further reduction of the ester is likely if you could find a reducing agent that does this selectively. That's asking a little too much of nature here. So the right idea was to reduce first and then use Fischer esterification to create the ester product.